And the next speaker is Chiara Ceccobello on the BHJET code. Go ahead, please. Thank you.
Hi, hello everybody. My name is Chiara Ceccobello, and I'm a postdoc at Chalmers University of Technology. Thank you, the organizer, of course, to give me the possibility to talk at this conference. I will be talking about today about the BHJET code, which is a code that it has been used for like over the years for modeling multi-wavelength emission from accreting black holes and neutron stars as well with jets. But today I'm going to present its public release. So recently, Matteo Lucchini and I and this list of collaborators and many more actually who contribute to the code made it into a final shape for the moment that we summarized in a paper that we recently submitted. And here you can see the link to the archive. And also we put the code, we made the code public on a GitHub repository that is also listed here. So what's the idea, the main goals of this code? Everything started with the idea of going beyond what the typical bumper conical jets is. Mostly because the model is based on the idea that we have multiple components contributing to the full electromagnetic spectrum from the system. So we want simultaneously to fit and constrain the spectrum from radio to X-rays, and we'll see that in the future also very high energy as well of jetted accreting black holes and neutron star systems. We would like to do that while incorporating the knowledge that we are obtaining from MHD studies and relevant codes that calculate similar things, maybe just in one band or multiple bands, and of course observational constraints that we get from observations and multi-wavelength campaigns. Again, we would like to do that while keeping the runtime acceptable for fitting. So that means that we would like to use semi-normal computers to run this code and fit data efficiently. And so, like I said, we recently made it public, and these are the links. So I'm not going to be able to go into all the features and all the details of what the code can or cannot do. So please, I invite you to read the paper and also maybe play a little bit with the code. Okay, this is a very incomplete history of the code, and I'm not going to describe every single milestone that you see in this slide. I just want to point out that this code, this model originates back in 1995 from a Falken-Biermann paper about this jet symbiosis. But then Sarah Markov took it on and actually shaped it into a proper code that does lots of things and has been used over the years on to fit AGN data, X-ray binary sources, and also most importantly was used to make for the first time the association between the jet base and the corona. And also together with Mike Novak, they made a study about the reflection signature of the jet emission, and actually gave a tool to discriminate between the X-ray emitting processes within this model. Then, of course, during the years, many people contributed in an even substantial way to improve the code. Most noticeably, Matteo Lucchini in recent years added a completely new flavor to the model. And since the scenario now became quite complicated together with all the other features, we decided to rename it into BHJET and dedicate to it a full publication that explains again all the new features and shows also examples of applications to X-ray binaries and also AGN, different AGN sources. Okay, so just to give you an overview of what the code and the model is all about, I'll start saying that we now have these two flavors. So the old flavor is the still named agent jet, which is now a conical jet, but has a jet nozzle base corona type of thing. And then further on in the jet, there is a region where we inject non-thermal electrons to produce the flat radio spectrum that we see. And it's like the agent jet is a pressure-driven jet fundamentally. Whereas in recent time as well, we added, Matteo added this BL jet, which has a region where magnetic acceleration and collimation happens, which terminates with the acceleration region further on. This part of jet is not conical anymore, and this is of course to be more in line with recent observations of AGN observations, but also as we heard about during this conference, X-ray binaries as well are showing hints of possible not conical jet shapes in several sources, and also they're showing that we're starting to see that maybe the lateral expansion of the jet is not as fast as we thought, because probably there is a collimating agent that keeps the jet more confined, and this can be either due to magnetic collimation or external pressure, or a mixture of the two. For what concerns the radiation part of the code, we take in consideration several processes, and so we have emission from the disk, and then from the jet base we have a thermosynchrotron emission, thermosynchrotron emission. These two populations of photons are then taken as seed photons for the inverse Compton scattering that happens along the jet in several regions. But then, as you can see here from the plot, the blue curve, like the dark blue curve, purple curve, is the part of the part of the jet that is closer to the jet base. Well before the first acceleration region, and this is the part where that contributes the most to the total jet, to the total spectrum of that we produce. And then from the acceleration region on, we inject this non-thermal electrons that produce the typical jet break and flat radio spectrum that is characteristic of compact jets in these sources. I would like to point out as well that there is a possibility to inject just right from the base a hybrid population of electrons. The non-thermal tail can be adjusted depending on the specific distributions that you take into consideration, and also with a dedicated parameter. And also, in principle, you could also do the same by moving the acceleration region very close to the jet base. But this is again to show that we have this kind of flexibility to be more aligned again with observations and recent modeling of corona in that sense. Then I would like to talk a little bit about the multiple inverse Compton scattering routine that I worked on. For this part of the code, I took a fairly simple approach, in the sense that I didn't perform a full radiative transfer calculation for this, but instead I took the inverse Compton kernel with a Klein-Machine cross section and iterated it multiple times until the spectrum converges to like its final shape, and so higher ordered would not make so much difference in the end. But of course, since like I said, it's a simplistic approach, we do not take into account many factors, and this in the end result in a typical, in an averagely, on average in a harder spectrum than what you would expect for a given set of parameters. So to, yes, thanks. So to milden that, we compared our spectra with a table of COMP-PS spectra calculated in the range of optical depths 0.05 to 3 and electron temperature 20 to 2500 kD. And then we matched our spectra with those and introduced this correction factor that again takes into account like terms like, for instance, the escape probability or like the pair content and so on. This is an example of a fit towards a bright hard state of GX to the -4 with the two flavors. I'm just really going to say very quickly that we get with this new code and the new features, we get much better statistical fits to with both flavors. And you can see that like the area of the parameter space that we end up with the two flavors is a bit different, even though the jets are actually quite similar, because things like the magnetization and so on are very make the two flavor very similar. But in one case, in the old case, like in the AGN jet version of it, we still get like a large jet base with a high electron temperature, low optical depth, even if more moderate than in the past. But then with BHJET, we get a more compact corona with parameters that resemble a little bit more the standard corona idea that we all have, and maybe even a lamppost geometry kind of thing. Then I will spend really a few words on the future step that I'm particularly fond of, because I've been working in recent years in calculating two grids of MHD jet solutions, both non-relativistic and relativistic, in order to substitute the structure, the dynamical structure of the jet in this code, and actually be able to fit the MHD quantities, the right quantities of the jet to a given source, and then calculate the radiation on top of this chosen jet configuration in this way. So please stay tuned for this. And then I will conclude by saying that another very important future step that we are it's ongoing is the inclusion of hadronic processes by Dimitrios Kantsas. He already published a paper on this, and soon will be part of the public version of the code. So I hope I sparked your interest about this code. So please take a look at the paper and also play with the code. Let us know if you need any help, and yeah, have fun. Thank you.
Thank you very much. We have time for 1.5 questions. Raise your hands if you have any. I don't see any in the room or online. I have a quick one. What's the timescale for the evaluation of one spectrum?
Well, I guess it depends a little bit on the source. The reason why we took this like simplified approach to the multiple inverse confidence scattering routine, for instance, is that the more scatterings you have, the more you're spending time calculating the spectrum. So that is the bottleneck point. You can still so if you're running the code outside the fitting process, it takes just like maybe a few seconds. Then of course, if you add the data and then you start fitting, then things get a little bit longer, but depends on the computer as well that you're using.
Okay, Jonathan, quick question only, please.
Yes, hi, Chiara.
Hi.
Great talk. And
thanks.
I must say that going forward beyond the Bluntford and Koenigsegg paper is a real must. So congratulations, and please go on. I have just a tiny question about the when you include the MHD and the self-similar. I guess it will be self-similar, right?
Yeah. Yeah.
So then you will have to choose. You will have to truncate the solution when it goes for the spine, at least for above the black hole, I guess. So what will be your strategy for that?
Well, so right now we are mostly focusing on the jet sheath, since what seems to be carrying the bulk of the radiation in any case. At the moment, BLJET can do can reproduce the spine fairly well. So I guess that in that specific case, we're just going to keep that in the code as well. Yeah, of course, the radial self-similar MHD solutions cannot go close to the axis. So.
So you will fill it in. You will truncate the solution down to some radius, and put inside some pressure, right?
Yeah, I would assume so. Yeah.
Okay. Thank you.
Thank you very much again.